Pipelines are humming, systems gonna overload. We got clusters making magic in the line. Funkified computing, baby.
Welcome. This is episode 2 of Cluster Funk. I'm one of your hosts. My name is Ed Fullman.
And I'm Fabrizio. Hello, Ed. Hello, everyone.
Hello.
Welcome.
So in episode 1, we introduced Kubernetes and talked generally about the value proposition. And now we're going to take a little bit of a deeper dive and talk about pods, nodes, and the control plane today. I think what we learned the last time, what we were talking about, was that Kubernetes is like the universe. It's like a universal orchestrator for technology infrastructure, and from that perspective, it's got a ton of value for people that want to do that kind of thing.
So, Ed, today we are going to look inside the cluster like it would be a surgery, but without doing the real surgery. And when we kill the cluster, it will be like a dead body surgery. I don't know if it's similar, but we are going to dive deep inside the components of the cluster. Where do you want to start from? I mean, I know that you already know Kubernetes, but let's do like it was something from scratch for you, and we start from pods, from schedulers, control plane, whatever. I would start from pods because they are the basic unit of deployments in Kubernetes, and they are generally confused with containers, but they are not really containers because they can hold one or more containers. So that idea of having a single container is something that everyone should remove from the preconcept that we have. And we have just the network that is shared inside this pod ecosystem. And they are basically sharing the same IP. They can have a lot of integrations. They are several containers, and they are basically the base of Kubernetes theory and deployment. So is that quite clear for you?
Yes, so pods are kind of like the apartment in the apartment complex. They're meant to. They are not meant to live forever. They're disposable. So it's really a capacity inside of a capacity.
And it's your app, it's your application. Think about that you have your application running in multiple pods, and if you need to scale the application, then you will scale the pods because you don't scale just the containers, but what is really containing the containers. And generally pods are not running alone, but they are managed in deployments, in stateful sets. It depends on what you want to obtain from that, because deployment is really volatile. You don't bother about the disk itself for persistence, while stateful set has generally a disk paired, so like databases and similar, that when you restart the pod, you don't want to lose the content of your application or whatever service is running on top of that, then you pair the disk, and it becomes something like a stateful set that is a particular characteristic of Kubernetes for the replication controller that is grabbing persistency. I would say that they are similar to sushi rolls. They are bento box that keeps them from rolling off the table. So it's just an analogy that maybe it will become fun if you think about food.
So when you think about pods in our deployment, how do you keep them separate from one another? Like, how do you tell one pod from the other? What has been some of the interesting things that you've had to do to get to scale up pods or things like that? Like when we run into a problem where we have to kill it, like when is that happening versus scaling versus other things that we do with pods?
So if you run pods on top of a node or something like that, then it will be something that you can move, kill. They are generally hosted in containers that is not really containers for this case. It's something that is an abstraction layer. So you can kill the pod. If you kill the pod itself and it's just declared, then it will be removed.
Mm-hmm.
But if you are having it in a demo set, it will run in a special inner resource that is called generally replication controller or replica set. Replication controller is a name that was present in earlier version of Kubernetes, and it was basically what evolved in a deployment. So the replica set itself is what is giving you the ability of having the pod coming back, having the containers after you kill them coming back and being healthy again if all the conditions are met. This is really a characteristic of Kubernetes that is unique because generally we consider the scheduler self-healing. So it is able to restore a specific state that you expect to have from orchestrating the resources just because you are able to revive it, having the status in the cluster effectively managed by these resources. And if they are in a deployment, the replica set that is under the cover, what is maintaining the pods up, will ensure that whatever you declared as available is there available for you. If they are in the stateful set, it's exactly the same concept, with the only difference that when you kill them, they will be reattaching the persistent volume that were there for persistence, the data that were contained in a disk, by the claim that is that resource that will be pairing the pod again to this kind of persistent information. And so, they generally go ahead.
So when you think about a pod with containers in it, is a pod get unhealthy, or does a container get unhealthy, or is it what's the give and take there that makes pod?
That's a nice point. Generally, it depends on circumstances, but when you have a pod that is a single container, that can be the case because generally we don't have a lot of containers inside the pod. But if it's a case that is just a container, then it will become unhealthy, and you know that that resource is effectively the one that is affected. But when you have many containers, like init containers that are just at the beginning performing some kind of operation that can be preparing a database, loading the schema, loading the data, whatever, or what more operations that you need to prepare and initialize the pod. Just the first time that you run it, so not when you restart, the init container will be just a one-shot. When you create the deployment, it will work. Or you can have sidecars that are providing additional resources, like in example, they can do the metric ability, the metric tasks that you need. They can be service mesh or whatever other thing that you want to pair as a sort of proxy in service mesh, in example, with Istio or Envoy. You pair a sidecar container. There are additional ways that we can do that in these days, but the initial approach was that one. So to your container, you paired additional ones. And for that, you need to rely on special readiness, liveness, health checks that are generally giving you the behavior that is failing or logs. And when you look for logs in a deployment, in example, or in a pod, why not? You will have, when you have many containers, to specify which one do you want to look at, because in each log for each of the running containers, there could be the reason for why they are unhealthy.
I see. So this is like the Russian dolls. So the containers are the smallest one. If you go out a level, you got pods. If you go out another level, you have nodes. So
the difference is that in Russian dolls, they are all nested. But
Yeah.
in our case, they can run parallel. So it's US doll. It's different from Russian doll.
So it's when we get to the node, that's the working machine, right? This it's either a virtual or a physical one, but this is like where an EC2 comes in, right? And that is what the where the node is. So what's the relationship, to put it to make a node on a physical or virtual machine? What's the process for getting those nodes created? And I would assume that the node comes first, right?
Yeah, generally you have several type of nodes. We can talk about worker nodes or agent nodes, depending on how the distribution is calling them, because in K3S or K2, there are some names that you give, but generally workers are where the kubelet and these pods are running. And there are then the server or master nodes where you have something like a control plane. The Kubernetes distributed factory, I would call it that way because it's a distributed system, is composed by these nodes that are the assembly lines. So every node generally will run the kubelet except for the master. But again, if we have K3S or K2, you can have mixed nodes, so you can run also kubelets on top of the control plane nodes, and they will communicate each other with the control plane via the kube proxy. So these kube proxies will have also the firewall rules like the IP tables if you are using that, or evolving to a different way of using the network. You could have some kind of eBPF integrations with the kernel and replace the network security with additional rules on top of that. Generally, these nodes are, you call them EC2 instances. Not necessarily. We are running in AWS in most of the cases, so they could be there. But it's really could be a bare metal node. So whatever you have, also a virtual machine that you create in VirtualBox and you run Kubernetes on top of that, that is just where the operating system is residing. You install Kubernetes on top of that. Depending on the node topology, you will run on top of that the kubelet, the control plane, the etcd database where the status of the cluster is ensured, or whatever other component is required to run the whole ecosystem. There is something that we will talk probably as soon as you have the clear concept about the nodes that are the kube proxy, the API server, the control plane, the etcd database, the kubelet itself. For the moment, think that we run those pods thanks to the kubelet that is very similar to a distributed Docker engine, but it's used by each node to create this interface with the containerd or the container engine for this case, because we are using generally containerd is the adopted standard, and it will be like running a Docker container on top of a Docker engine. But it's controlled by the kubelet that is understanding how Kubernetes works. So it's preparing everything that you run as a container to talk with the kube proxy that is generally relating to the control plane. So it's like still the Russian dolls, but parallel, because it's distributed. Russian dolls are nested. And we are talking about something that you have to look in a wide line, like the horizon is just the limits for Kubernetes to exist, what you can see. Like the pizza ovens, you can load a lot of pizzas and eat them together, but generally you do that in a different way because you want a lot of people to access the information and to eat the pizza.
So the last piece that we were going to talk about today, and we can kind of piece it all together after, is the control plane, and how that, as a control plane, makes decisions, tracks state, applies what we want done to the process. and it's going to do it properly or improperly, depending on how we set it up. Inside that control plane, we've got the API server. This is kind of the front door to everything. Everything talks to this. The scheduler, which decides which node gets what pod. So that must also be talking, or maybe it isn't. I always learn something new. So does the kubelet talk to the scheduler? Is that what it's doing? Or because that's the air traffic controller, the scheduler. Is there a relationship there between the node kubelet or the proxy and the scheduler?
The scheduler is something that you have to think about independent. So it seems crazy, but when you do the exams for certifications, in example, they will ask you to create something like a controlled scheduler, because you can declare in the manifests of Kubernetes what you want to do with the scheduler. And it's really up to you. You can control the scheduler also independently from the control plane. Generally, it is controlled by all of these components because it's part of the control plane, so it's a main component. Then you have the controller manager that is really reacting to that. But you can have a personal configuration of the scheduler. And how you do that is just running a specific modification on top of the scheduler manifest, especially if you are using a distribution that is similar to what is QBADM, that is the probably most known distribution for do experiments. You can create your own scheduler, run your own scheduler on top of that, and it's literally how you schedule resources, how you want the cluster to do something with your ability to schedule resources on top of that. Different thing is the API server. So the API server is where the control plane is receiving and sending all of the calls that generally are coming from the kube proxy and from the kubelet running on top of each node. At that point, you understand that it's the centralized brain, like you said, and it's receiving and sending controls to ensure that all of the resources are controlled via this API.
So when we have like a multi-cluster control plane, right? And something like we've done between the cloud and the edge, for example. What's the difference there? I mean, how is that supported with the different technologies that we pull together here?
So multi-cluster is intended to be something that will have several clusters. And for each cluster, you will have a special, separate, dedicated control plane, because the control plane is really limited to one single entity. That could be, for our case, a cluster. At this point, it is really what is the boundary. So if we have multiple clusters, we will have multiple control planes. There are ways, like an example, if you have been using EKS or AKS, the abstraction layers that they created for us, we will not have the control plane. It's managed by the provider of the service. You just use the nodes that are running the kubelet and the kube proxy on top of them, and you don't see the control plane or masters. They are just controlled by the provider. How the provider is controlling that? They could have a sort of cluster, additional one, with multiple nodes, but having multiple control planes on top of a cluster of master nodes, and they will separate the offer. There are ways to split the control planes management on top of a cluster of nodes. So a pool of masters, maybe better to use the terminology pool in this case, pool of masters that are controlling several node groups that are controlled by a single control plane for each of the customers.
That's cool. So I didn't realize that in a multi-cluster environment, there isn't a shared control plane, but it makes sense because they'd be separated by network and other things. So you wouldn't have one control plane for it all.
One
So-
example, in our use case, generally, we have been working together on something that is cloud, then we have an edge node. But those edge nodes are real clusters. One edge node has one single control plane that is completely different from the control plane of the cluster on the clouds.
Right. Who are some of the? I know we know some people that have been working on some control plane products, or what's the name of the company project I'm thinking about, the CNCF project.
There can be many. Generally, it's commercialized because there is one that is called Kamaji, and it's an open source project. It's done and maintained by Italian people, so like
So
me.
must be good.
It's a mafia component, and it's generally Plastics is the company, and Kamaji is this kind of abstraction layer, but there are others. So now I don't recall the name. You can find a lot of abstractions in the control plane as they are managed outside to split the control to many clusters as a single provider. It's generally what you would do if you are thinking to be a provider. If you are just a user of Kubernetes, there is really no reason to do that abstraction if you are running your own bare metal or you decide to use this kind of external services. If you want to separate development, QA, production in a sort of approach that will be, okay, let's create a master pool to have several control planes and then we relate to them with different CD stages, or you want to manage, but at that point you will become a provider, your customers to have separate control planes to ensure more security, then you will create something that is very similar to EKS, or the cloud provider solutions, and you will need some products like Kamaji, an example, that can do that with a UI. You will create segments and 3 virtual master nodes to manage a pool of nodes for the agents and the kubeproxy and kubelets, and you will have that abstraction effective.
So going back to our distributed dolls, right? Not nested. When we pull this all back together again, the control plane's purpose is to notice something's wrong, I suppose, and start the process for recovery. Is that what the control plane's going to be doing in this case if something breaks?
Well, we generally hope that nothing is going wrong, but you are right.
The day it's
in
not.
Kubernetes, we use something that is called reconciling. It's not husband and wife. It's a different type of reconciliation. It's a reconciliation between the state that I would like to achieve. So something that I declare by manifest, I say, I want this deployment to be up and running and to be healthy. And this is declared in something that is under the control of the control plane. It's called the etcd database of the state database. It's like a world status or world state of the cluster. You want to ensure that what is written there is really what you have at the behavior of the cluster wide. So that is the purpose of the control plane. It will ensure that what you have declared is maintained. To do that, the controllers, generally there are several controllers. There is a master one that is responsible of looking at the Kubernetes main API, where deployments are declared, stateful sets, whatever resource that is available with Kubernetes itself. When you write your own operator, so you extend that API for your needs, and you write additional resources, like you could call a resource Kafka clustering example. It's like the operator will do, it will define a Kafka cluster, and it will know how to manage that. It will become another controller that is a separate one from the main controller, and they will look at that etcd database where you declared the status that you want to maintain, the state, and check if the consistency of the resources out there running on top of the workers are effectively what you expect to be. So that will be the reconciliation, not between husband and wife again, but between a lot of friends that are acting as the same entity controlled by the control plane. You said at the beginning it's a control status. Maybe it's more not a dictator, but it's similar because whatever the control plane will ensure to be maintained, that will be because of the declaration you did in the etcd database with your manifest and the creation or deletion of resources.
And this all cascades down from the beginning, which is the description in the YAML file, right? That's what drives all of this control that is going to be done by the control plane.
And when you think about that, it's declarative. So in DevOps, generally, we have that separation between imperative and declarative. The imperative way should be scripting. Declarative should be creating YAML files to describe a context. The control plane is imperative with declarations. So it is ensuring that what is out there is exactly what you declared. So you are declarative, but the control plane is acting with more control, not really imperatively because you are not writing scripts on top of that, but it's ensuring this kind of behavior.
That's when we get into challenges for pods crashing, nodes going offline, does that cause challenges in the control plane that can bring everything down, or is that generally kept separated and protected as the control plane when things go wrong?
It's for happy life maintenance. So think that when you have a crash, the initial idea will be, okay, I power off my machine. I haven't seen it. I go out, jumping in the grass out there, and I will not think about that. But at the same time, you have to take some kind of countermeasure. The control plane, if there is a constant clash, or let's say the Kubernetes ecosystem having a constant crash of resources, will be affected by a recurring behavior that will consume resources. So there is a way to increase a threshold when you control this crash, and it will become, in example, crash loopback. So once it started to crash for 10 times or a number of times, an undetermined one depending on the configuration, it will be left there. And you will have the error. The behavior will not be what you expect in the happy path, but it will be in evidence because you have something that is crashing and it's frozen. So to avoid this enormous amount of resource consumption, then in security, we could call it denial of service. To prevent that, we have an increase in latency and we leave it there crashing or crashed, stopped, because there is no reason for restarting it if nothing changed. And this is a very powerful concept. So I can restart it as many times as you want. It is affecting me because I have to do something that really it's nonsense because you changed nothing. So it will keep crashing. At that point, it's left there and it's saying to you, fix that or it will not start. This is a nice way of scheduling resources by an intelligent scheduler that is not really like AI, but it's a logic consequence. So it's crashing. You change nothing. It's there, left there.
The reason we do this, have Kubernetes in our life and rely on it is because it does give us the ability to create resilience, scalability, and automated recovery. I mean, it is a grand system from that perspective, finding its way into everything. I was talking to someone recently, who was looking at a problem where inside of a telecom switch, something that used to be very much about embedded firmware and how very specific coding to make it work, now has Kubernetes inside that switch. And they're using it to orchestrate multiple switches together and everything, which is a huge change. So I think Kubernetes is out there changing our life, whether we realize it or not. It's probably affecting everybody at this point. They just don't see it because it is resilient and scalable and automatically recovering from problems.
Yeah, it's for sure a powerful concept because, again, think that we are not having artificial intelligence, but we are realizing that if nothing is changing on an ecosystem that is not ensured because of a wrong configuration, an error, and no one is acting to change that behavior, the scheduler simply stops doing things to recover and we just let you know. There is this crash loopback that after 5 minutes, in example, or an increasable amount of time, will retry that. Like saying, let's say that is similar to Windows 95. Blue screen of that, let's do a restart.
Yeah.
And Kubernetes will still use that old concept that it was, okay, it will start maybe because something magical will occur. But the reality is that if you do not operate the right change to have that effectively working back, there is no automated recovery. The automated recovery of Kubernetes is, in example, if the network connectivity goes down and you don't have communication and the service will start crashing because the missing resources on the other side, when the communication is back, this automatic loopback will restore the service, you will have the condition back, and it will become available again. But if it's something that is not changing, there is no reason to operate a change. So the automated recovery, I would say it's a controlled automated recovery, is by events, like Kubernetes is, because etcd is saving the status, the state that you want to achieve, but it is also containing all the events that are consequences of what is happening in Kubernetes out there. That is a powerful way of event-driven applications and infrastructure management.
Well, that's it for episode 2, pods, nodes, and control plane. We're out of time. Again, my name's Ed Fullman, and this is
Fabrizio.
He does know.
I was thinking about Kubernetes, what we talked to today, and the fact that we haven't transformed really this information in something that is a language. So people that will be pragmatically thinking about how we control all of this. I think the next time we could talk about YAML, yet another markup language that is very used, the JSON implications, Helm, the GitOps things that we can do with Kubernetes, and transform this kind of abstraction with, I said husband and wife earlier.
Get into trouble.
We are not, yeah, we can get in trouble.
Well, thanks a lot, Fabrizio. This was an interesting discussion. I think people watching this will learn that understanding these fundamental concepts from the inside really sets you up to understand, how to build and create Kubernetes solutions. And next week, like you said, we'll get into how we actually use it and do a lot of things that are very cool. So thanks, everyone. We'll see you later.